The following content has been provided by RWTH Aachen University.
So now going to the information content that you guys have, so leaving the Gestalt laws a little bit behind. This is an approach to get the theory of bits and bytes back to your user interfaces. So trying to model the information channel capacity that a display has or an interface has. And so there we have the basic unit of information also in bit. And this task is not always easy because, well, humans aren't binary in a way. So there are much more information underlying there. And this tries to just give you an idea, well, how much information does this interface actually communicate to the user. And yeah, should pay attention to that, keep that in mind. Last year's often people forgot about this. Hint. So keep that in mind. For example, if I have a regular toggle button, how much information do you think I can process with this? I can communicate with this. Yes? 2 bits? So if I would go then to, if I have the bits from the theoretical computer science, how much information does 1 bit have? One bit actually then has two states, or it can be 0 or 1. So if you go for, then it's just 1 bit, yes. So a toggle button has 2 states. It's either off or on. And so we would calculate this by getting the logarithm of the different states. So in this case, we have 1 bit. And keep in mind, it's not the physical storage capacity that I need to store the blue box with a check mark in that. It's actually just the amount of information that this transmits to you. Okay, so another example, if I have just a single digit, how much information does this provide to the user? Yes?
About 10, from 0 to 9. That's 1 digit.
That is the different states that we're having, yes. So I have 10 states from 0 to 9. And the amount of information that I have here, if I would calculate it into bits. Yes? 4 bits. How do you get to that number?
When I round it to the next power of 2, and then that would be 16, so the logarithm is 4.
Okay. Yeah, so you could take the logarithm of 10 and actually get to 3.3. You said, well, I rounded to 4. Why did you do that?
Because we can't really, I don't know how to say that. Because we don't really have 0.3 bits in computers, but maybe in information.
Yes, and if you would go for just the engineering approach, this would be correct. The thing is, keep in mind that this is not the engineering side of that. So, of course, if I want to represent that in my system, I need 4 bits because I can't store 3.3. But the information content is still only 3.3 bits because I just have these 10 states. So the 6 others that I have, well, they wouldn't be needed or are not needed from the 4 that I would have to store physically. If I would have hexadecimal number or all these states, so from so 16 states, then yes, that would be correct. I have 4 bits of information that is processed by the or transferred by this number. But for this, it's only 10 states, so it gets down to 3.3 bits. Next one, if I just have single letters, upper and lowercase, so no fancy additions there. Just the upper and lowercase of the basic. Yes?
So there's the logarithm to the base of 2 of 52.
Mm-hmm. Yes, you don't need to calculate that. So yeah, I have 52 states, at least last that I checked, we have 26 letters, if I'm not mistaken. And yeah, the logarithm of 52, I get to 5.7 bits that this information transfers to the user or communicates to the user. Yeah, so what to keep in mind, what this means is the capacity of the information channel from the UI to the user. How much information does the UI transfer to the user? Yes?
Why do we use the base of 2?
Yeah, as we're trying to model the bit approach that is, yeah.
But still, you know, human is not a computer, so why to compare it to computer so much?
Well, because we're trying to communicate what the computer offers you to get it more into the theoretical underpinnings of computer science in general. Because everything computer science runs on these bits, and this is a version or a approach to model the information that a UI perceives to you in this underlying model of bits.
Okay.
All right. So up to now, we had this nice digital world where I have 2 states, 10 states, 52 states. What do you think will happen if I have an analog scale? So, for example, this 1/3 of a cycle, of a circle, and what do you think the information content in here? How do I find that out? Yes, down there.
Theoretically, you have infinity number of states, so you need to decide what loss you will put them together. So if you have 27 just 2, you can say the left one is the 0 and the right is the 1.
Mm-hmm. Yes, and that is basically what an analog scale can do. It could show you more or less infinite amount of positions. But to get the information, what this transfers to the user, they did a couple of experiments where they just tested how many different states can a human actually distinguish automatically. And what they done was started with 3 states, so they showed one pointing here, one pointing here, one pointing here, and presented that to people and asked them, well, what does it say? Is this the first one, second one, or third one? And they looked how often people got that right, so they could distinguish between each of the states. And then they continued that, for example, with 8 states, and had just gradually more positions that the dial could actually show you, and try to figure out, well, how many different positions can people distinguish directly. So recognize, well, this is this state, this is that state, and differentiate between them. And what they found out is that, yeah, actually with 8 different positions, people can distinguish them quite easily, or can distinguish them more often. And yeah, that gets then down to an information content of 3 bits that I can show with the dial. Yes?
Does it depend on the size of the scale?
I think if you keep it at 1/3 of a circle, this will stay roughly the same. But if you add, for example, markings here, then the possible positions, they actually increase, because you can put it more into perspective. Well, now I'm about half between these 2, So you can differentiate even more positions if you have additional markings there. Yes, but yeah, that is now all visually. We can get now to audio pitch or volume or the salt content. So audio pitch, the different pitches of notes. What do you think? How many different positions can humans differentiate there? Yes? 8? So 8 different pitch positions. In bits, so you would say around 2. 3. What about you?
I think our ear ability is much more sensitive than we expecting that.
Uh-huh.
I think we can hear something about 20 megahertz to, I don't know how big or how it is,
Mm-hmm.
but we can, I think, differentiate between two different tones by 1.5 megahertz difference, I think.
Yeah.
But I'm not really sure if this is true.
Yes, so that is more about the range where we can hear stuff. So if I would get it to this example, would be the range where I have these sliders. And with the same experiment or the same setup where they played a sound with a different pitch to a participant in a user study and asked them, well, what is it? Where does it belong? They found out that it's actually 2.5 bits, so quite close there. But of course, as we already mentioned quite a number of times, it's different between people because you have also people that have perfect pitch. So if they hear a note, they can say, "Well, what? A flat," so they can immediately pinpoint what tone is it. And for those people, they actually have the possibility to distinguish between 5 to 6 bits of different positions there. So getting to the volume level that we perceive, what do you think? What is the information content there? Any guesses? I want different ones. What about you? Yeah, second row, middle. Just any guess? How many information?
I'm not sure.
Not sure. Good answer. Will work. Would you say it's less or more than what we can differentiate with pitch? More? Less? So we have all of that. Basically, a whole range of stuff. And the thing is, it's actually a little bit less. Because what your ear is designed to do, it automatically tries to level the volume, tries to adjust that. You might have experienced that when you were in a quiet room and afterwards you put your headphones back in, it's just blasting. And then another occasion you're in a crowded room, everyone's talking, it's quite loud. Then you go out, put them in, it's the same volume, but you have trouble hearing that. That's because your ear or your brain automatically tries to adjust the volume. And this actually, in this case, leads there that you can't distinguish as many different positions reliably. And yeah, the last example, saltiness. So Professor Borchers has this great idea of a new gadget that you can lick to get the amount of emails that are in your inbox. So when you want to know, well, do I have any emails to read? Just lick it, and from that I know how many there are. Patent pending. What do you think? How many bits of information can we distinguish for saltiness? Yes? 1 bit. So more or less two states. It's there or not there. Yes.
There is salt or there is no salt. We can taste if there's very, very much salt or just an okay content of salt or no salt.
Yes. So a bigger range than just it's there or not there. And actually it's quite close to 2 bits, but it's more we can find out there is something, there is salt, it is salty, but then just roughly how much it is. So not very a big information state there. So might have to rethink that idea. Although it would be quite interesting. I think no one would borrow your phone anymore, though.
This content was provided by RWTH Aachen University.